Hi, in this video, we want to take a look at probability inequalities. Okay, the big concept here for probability inequalities is that I'm in a situation, I need to analyze mathematically, theoretically, I need to analyze a probability distribution. But it's too difficult for me to do directly, that the math is just maybe not tractable. Maybe there isn't a solution. Maybe it's too complicated. Maybe I don't have enough information about my distribution. So what I want to do, I want to take the information I have, my knowledge of standard deviations, my knowledge of expected values, my knowledge of probabilities, and come up with a weaker statement than what I would want, but one that's good enough for the analysis I'm doing. I want to get insight into what's going on without having to use really, really complicated math. I want to take a simpler, easier mathematical statement to get information that's good enough for my purpose. Okay, so probability inequalities give us a way to analyze random variables when direct analysis is not possible. All right, so we're in a theoretical statistics, theoretical probability situation, and I can't solve the problem directly. Okay, so what I want to do, I want to somehow use math, other aspects of math, to figure out a statement about this. All right, so we're going to go over three inequalities. First one is Markovs inequalities. What this does, this connects central tendencies to probabilities. The next one is going to be Chebychevs Inequality. Now, Chebychev's name doesn't have really that great of a direct connection with English. So if you look this up in different books, different websites, you're going to see different spellings and also different pronunciations. His name is not in my native tongue. I was always told it was Chebychevs. I've heard plenty of people say it differently. I'm going to say Chebychevs. All right, so what this does, this connects the spread of the data to probability. Now, Jensen's inequality helps us analyze expected values in terms of convex functions. All right, so if I start digging into some aspects of calculus, I have integration, and which integration is a limit every single time. Well, anytime I have anything involving infinity, I cannot switch the order of things. This is an unintuitive aspect of infinity. Because of that inability to switch the order of integration and functions, sometimes we can't analyze things directly. Jensen's inequality gives us a way to get around the inability to switch so that I get good enough information for my purpose so that I can move on. I have insight into what's going on. Okay, so first one, let's look at Markovs inequality. This connects central tendency to probabilities. Okay, so what we're going to do, we're going to say that G is a non-negative function. So G is a non-negative function, so we're saying that G is greater than or equal to 0 for all possible x, okay? And we're going to say that x is a random variable in the domain of G. So anything I get from my random variable, I can plug into G. All right, then what's going to happen is that the expected value of G of x divided by A is greater than or equal to the probability of G greater than or equal to A whenever A is a positive value. Okay, so remember that G is positive or 0, and so this statement would only make sense if A is going to be positive. Otherwise, we won't even worry about it. Okay, so how are we going to do this? How am I going to prove to you that this is a correct mathematical statement? Okay, so what I'm going to do, I'm going to take the expected value of G. Now, I'm going to break that up into two parts. So either x is less than A or x is greater than and equal to A. Okay, so I'm going to break it up into two parts. The first part is going to be when x, this here is, I'm considering the situation where x is less than A. Over here, I'm going to consider the situation where x is greater than or equal to A. And I'm breaking up the expected value. Now, this follows directly from how we define expected value in terms of integration in calculus. And if you just go through and start doing the pencil and paper, you'll see that this will work out. Okay, so now think about the fact that G is never less than 0. So it's greater, G is greater than or equal to 0. All right, well, that tells me that this inside that expected value has to be greater than or equal to 0. Okay, well, the expected value of something greater than or equal to 0 has to be itself greater than or equal to 0. Okay, so now let's use this. What I'm going to do, I'm going to replace this part of this equation. I'm going to say, I know that that has to be greater than or equal to 0. Okay, well, if this is greater than or equal to 0, over here, this is a positive number or 0. This is a positive number or 0. And this is a positive number. Then I know that this part here, this whole thing, has to be greater than or equal to this, where you see that I've replaced one part with 0. So this part here has been replaced with 0. All right, so I know I took this and I replaced it with a smaller value. That means the whole statement on the right of that equation has to be less than what it was before I made that replacement. Okay, so that tells me that the expected value, so here we have the equal to all this stuff here. I replace this part, therefore everything on the right is less, which means that this has to be greater than what I have here after I've made that substitution with 0. Okay, so now 0 times anything is 0, correct? So all of this, I can replace, that part here, I can replace with 0 right there. Okay, now 0 is a beautiful number for addition, right? Because I just drop it. All right, so now I've rewritten this so that the expected value of G is greater than or equal to this probability of G greater than or equal to A and this expected value. Okay, well now let's look at this part right here. I look at that and I realize that I'm conditioning where G is greater than or equal to A. All right, so in this conditional part, G is greater than or equal to A. That tells me that this part has to be greater than or equal to A. Well, it follows that the entire expected value has to be greater than or equal to A. Okay, so what I'm going to do, I'm going to replace this part with A because I know that this has to be greater than A. So what I'm doing again is I'm doing another inequality that I'm shifting farther in the lesser direction. So I'm taking this term here. I know that it's greater than A. So that tells me that this whole part has to be greater than or equal to this whole part. Huh. All right, so I know I'm chaining these inequalities. This is greater than the middle part, which is greater than the part on the right. All right, well, that tells me that the part on the far left has to be greater than or equal to the part on the far right. So I'm just going to focus on those two. Boom, I'm focusing on these two. So now we know that the expected value of G is greater than or equal to this probability times A. Now I'm going to divide both sides by A. Boom, we got Markovs inequality. Now remember that this has to be an expected value of a non-negative function. Now, something that's interesting is I didn't specify the random variable, did I? I mean, I think, the inequality works for any G regardless of the random variable. Okay, so that's what makes this powerful. So we lose information because we're using inequalities instead of equal sign, but I have this added flexibility because I don't actually need to know what is the true distribution. At times that distribution may be so complicated that I can't actually tackle this. I can't dig into it. I can't get at it. And so this, I go, you know what? I don't even need to know. I'll just get around it. Ha ha, suckers. All right, so now let's take a look at Chebychevs inequality. All right, so previously Markovs inequality connected probability to central tendency. Now we're going to connect probability to the spread of the population. All right, so what we're going to do, we're going to say that X is a random variable with mean mu, standard deviation sigma, and then K is just some positive number. And we really don't care what K is for the moment. We just know it's some positive number. In this situation, the probability that X minus mu absolute value is less than K sigma is greater than or equal to 1 minus 1 over K squared. All right, what does this tell me? This gives me kind of an idea of how likely it is that X is close to its central tendency. Flipping it the other way, this gives me an idea of how likely X is to be far away from its central tendency. Now, something about this, I don't actually know what the distribution of X is. This is very powerful. All I need to know that it has an expected value, mu, and I know the value mu, and it has a standard deviation, and I know what that standard deviation is. And then this works for any positive K, any of them. All right, so now we're going to prove this using some integral calculus. Okay, so I'm going to start with a variance formula. I'm going to start manipulating that through to get what I want. All right, this is going to look ugly, but just go with me, just one step at a time, baby step it as much as we can. All right, so we know that the variance is going to be the integral of X minus mu squared over the entire real line for a continuous random variable. And we can modify this to be to work out the same way for a discrete, but I'm just going to show continuous. Okay, so now we're going to break up that integral into 3 parts. What we're going to do, we're going to go, basically there's a far left part, a far right part, and a part in the middle. All right, so we're breaking up the real line into 3 parts. Well, what are our cutoffs? Our cutoffs are going to be mu minus K times sigma and mu plus K times sigma. All right, so the first part is going to be everything to the left of mu minus K sigma. The third part is going to be everything to the right of mu plus K sigma. And then the middle part is what's in between those cutoffs. All right, so here is our far left part. Here is our middle. And here is the part to the far right. Okay, so now for the moment, just look at that middle integral. All right, so here, I'll focus on this part. I notice I have X minus mu squared. All right, so I'm squaring something, right? If I square it, can it be negative? No, it can't. So I know that the part inside this integral has to be greater than or equal to 0. Well, if this is greater than or equal to 0, the middle part, the parentheses is greater than or equal to 0, and f is always 0 or positive because it's a probability distribution function, then I know that the integration has to be greater than or equal to 0. All right, so then boom, I have that this integral is greater than or equal to 0. So what I'm going to do, I'm going to use the same trick I did with Markovs inequality, is that I'm going to take this whole junk here, all of this business. I know that the middle is greater than or equal to 0. So I'm going to say that sigma squared has to be greater than or equal to this, where I put 0 in for the middle. And you'll notice it's a simpler statement on the right. So here, all this junk in the middle gets replaced with 0. So I know that sigma squared has to be greater than or equal to what I have in this over here. Now, you'll notice that compared to the 3 parts that are split up, this is a simpler statement. Okay, now I'm going to look at the 2 outside terms. These are the ones that are spread out away from the central tendency. I look at this and I realize that because of where I'm cutting the number line, I know that X minus mu squared has to be greater than or equal to K squared sigma squared. So this comes from the fact that I know that I'm either far to the left of mu minus k sigma, or I'm far to the right of mu plus k sigma. If you work with it a little bit, you think about it for a little bit, you'll see that this has to be the case, that this inequality is true. Okay, well, what I'm going to do, I'm going to do another inequality step where I know that this part has to be greater than or equal to this. The only difference is that I'm replacing this parentheses squared, the parentheses squared is getting replaced by k squared sigma squared. I'm going to do the same thing over here. I know that this has to be greater than or equal to k squared sigma squared because of the interval of integration we're on. So it has to be greater than that. And so this part, the entire integral of this, has to be greater than or equal to that. So now I've done another, making it lesser step, but you'll notice that this is a simpler mathematical statement. I have fewer x's running around. Okay, so now I drop the 0, just because the 0 is not doing anything for me, to get this statement down here. Now I look at this and I remember from calculus, if I have a constant value, I can factor it out of an integral. Okay, so I can factor out an integral. So what I'm going to do, I'm going to go ahead and do it. And the reason why I can do this is because there's no variable inside here. These are constants with respect to x. So now I get to here. You'll notice I factor this out. I factor this out. Now I notice that I have a constant times both of my integrals, and it's the same constant. So now what I can do, I can go ahead and factor the constants. So now I have k squared times sigma squared times the two integrals added together has to be greater than or less than or equal to sigma squared. Okay. So now I'm looking at this and I realize I have a probability distribution function inside the integral, and I know from the definition of probability distribution functions that this is going to be a probability, this integral, and this integral is a probability. So let's go ahead and do the replacements. So now I've simplified the statement to sigma squared greater than or equal to k squared sigma squared times a probability plus another probability. Now I'm going to do a little bit of college algebra with my inequalities. I'm going to subtract mu from both sides and set things up. And so here, these two statements are equivalent to each other. I just moved mu and I dealt with a negative sign in front of k sigma. Now I look at this and I realize I have two mutually exclusive events and I have probabilities. Well, I can bring them together. So I'm adding two probabilities for mutually exclusive events. It means I can pull both events into one probability statement using a union. And boom, I do that. All right, so now I look at this and I notice that I'm saying negative x minus mu greater than or equal to k sigma, and I've got x minus mu greater than or equal to k sigma. I look at that for a moment, I go, huh, that reminds me, these two terms remind me of absolute values from college algebra. So what can I do? I can rewrite the statement this way. So here I know that it's this greater than k sigma or this greater than k sigma, and I realize that this actually corresponds to absolute value greater than or equal to k sigma. Boom. All right, so now I've made this a much simpler statement, you'll notice. So here, it's a relatively simple thing to be looking at. But let's take it a little bit simpler. Let's make it as simple as possible. I'm going to divide both sides by k squared sigma squared. All right, so now I have the probability by itself, and I have a bound on it. Now I notice that I've got a fraction with sigma squared on top and bottom. So let's go ahead and just simplify that fraction. Now I notice that I've got a probability greater than k sigma. So what I want to do, I want to use the fact that events add up to 1 in a probability space in a partition. And so I'm going to go ahead and take 1 minus thing on the left, 1 minus the probability on the right. Now remember, when I'm subtracting, I multiply both sides of an inequality by a negative, the inequality flips. So I can go 1 minus 1 over k squared, 1 minus the probability, and I flip the inequality as part of it when I multiply by the negative sign. And now I realize that this is the same as the probability of x minus mu absolute value less than k sigma, and I get Chebychevs inequality. So now this gives me a bound on, or gives me an idea of how spread out my data can be in terms of standard deviations, even though I don't actually know what is the distribution itself. I just need the expected value, I need the standard deviation, and I can figure out this nicely. Now, the next inequality we want to look at is one that involves convex functions. Now, a lot of introductory calculus classes call convex functions concave up. It looks like a smiley face, kind of, in my calculus class. All right, so here, when do we use this? I want to take the expected value of a convex function on a random variable, but I can't work through this. I can't get all of this down. What I want to do, I have the ability to handle the function on the expected value, but I can't handle the expected value on the function. So what Jensen's inequality gives us is that the expected value of the convex function, the expected value of g, is greater than or equal to g of the expected value. Okay, now notice it's not an equal sign. That's important on this. This is not an equal sign, it's an inequality. Okay, so here's an example of Jensen's inequality, and this is a rather simple one, but variance for any random variable, whenever it's defined, has to be greater than or equal to 0. Okay, so let's do this. We have a variance formula where the variance of x is equal to the expected value of x squared minus the expected value squared. Boom. Okay, so now I realize from calculus 1 that x squared is a convex function. It's concave up. Okay, if I take a second derivative, I'm going to get a positive value. And so I know that since it's a convex function, the expected value of the function is greater than or equal to the function of the expected value. Okay, so this statement is true using Jensen's inequality. I'll subtract both sides by this. So I know that this has to be greater than or equal to 0. Well, I look at the left-hand side, that's just the variance. Huh, boom, we got the variance has to be greater than or equal to 0 every single time. Interesting. All right, so now to get involved with the inequalities, we're going to go ahead and apply this using Chebychevs inequality. We're going to say that x is any random variable with mean 28 and standard deviation 4. What we want to do, we want to take Chebychevs inequality and find c such that the probability of x minus mu, absolute value, greater than c, has to be less than or equal to 1 over 10. All right, we want to use Chebychevs inequality to get this as precise of a statement as possible. So what we're going to have to do, we're going to have to figure out, we have to use this 10 to figure out a k, and then we use the k and the standard deviation to figure out the c. And then we're going to put our results into a document and upload the document into Canvas. Well, that's all I've got for you. Take care and goodbye.